In the last lesson, we talked about intermolecular forces of attraction, and we went through this worksheet where we looked at all the different molecules, and I walked you through some of these. Others you worked on independently. Hopefully, you were able to check out this key. If you did not, please do so because that's going to be helpful. Should you be able to, it should allow you to help figure out how you got different questions either wrong or whether you got them right or not. So take a moment to go through that if you have not already done so. But what we're going to do is we're going to take this idea of intermolecular forces of attraction and I'm going to apply it. Well, what we're going to apply it to is we're going to apply it to something that's called vapor pressure. And vapor pressure is exactly like what it sounds. It is the pressure, the force per unit area that a particle exerts while it's in the vapor or gaseous phase. Now, the vapor pressure is dependent upon the intermolecular forces of attractions because the stronger a particle's intermolecular forces of attraction, the lower the vapor pressure. Let me say that again. The stronger one molecule can hold on to its fellow molecules, the less likely that particle is to go up and leave the liquid phase and go into the gaseous phase. So if you look at the four compounds that they have listed here on table H, which is in your periodic tables, the four substances are propanone. Propanone, another name for propanone is acetone, something that's the main component of nail polish remover. Second one is ethanol, and ethanol is the alcohol, is the least toxic of alcohols. It's the alcohol that are found in adult beverages. And yes, I did say it's the least toxic of alcohols. All alcohols are toxic. Ethanol just happens to be the least toxic, but it's still toxic. You know that because it kills brain cells. It does all sorts of things to you. The next substance is water, and water is a very polar molecule. Um, Very polar molecule, and it has strong intermolecular forces of attraction. And then there's another particle here. Move my mouse. It's called ethanoic acid, and ethanoic acid is the primary component in um, in vinegar. Vinegar is called ethanoic acid or acetic acid. Pure acetic acid um, is not vinegar. Vinegar is, I think it's a 10 or 15% solution of ethanoic acid in water. But regardless, ethanoic acid has the strongest of the intermolecular forces of attraction, so therefore it has the lowest vapor pressures. Propanone, being a nonpolar molecule, acetone's a nonpolar molecule, is going to have relatively weak intermolecular forces of attraction. It's not exactly, it's not 100% nonpolar, but it is pretty symmetrical. But there is a component, it's called a functional group in the middle, that does create a slight dipole. And because of that, it is, I guess it's not fair to call it nonpolar. It's a weakly polar molecule. And because of that, it's going to have weak dipole intermolecular forces of attraction between it and its component molecules next to it. So as we look at these four molecules in succession, propanone has the weakest intermolecular forces of attraction and therefore the highest vapor pressures. Ethanoic acid has the strongest intermolecular forces of attraction and thusly the lowest vapor pressure. Table H shows you these four vapor pressures of these liquids and they give you a couple reference points. Down along the bottom is the axis with the temperature. There's also a dotted line here, and I've highlighted it with a green line here so it stands out. It's just slightly above the 100 kilopascals line, and that's because that line represents normal atmospheric pressure. Normal atmospheric pressure is 101.3 kilopascals, or 1 atmospheres, or one of the other myriad of units bars and torrs and millimeters of mercury and inches of mercury and all sorts of crazy things. But we're going to talk about in science, we're going to talk about 101.3 kilopascals of science. Now, why is that line important? Well, the line is important because what that does is that shows us, and I've marked the points here with 4 individual points. I've marked those points because those points are the boiling points of those 4 substances. So if you consider, like the one you probably know is water here, this third line here. Water crosses 101.3 kilopascals. It does so at 100 degrees Celsius. And that is the boiling point of water at normal atmospheric pressure. The boiling point, the definition of the boiling point, that's when the temperature of a liquid, that is the temperature of a liquid where the vapor pressure is equal to the atmospheric pressure. If you get those two things the same, the substance will be changing into a vapor as the atmospheric pressure pushes it back into the liquid. So it's going to be coming out of the liquid phase into the vapor phase at that temperature, and that's the boiling point. And so if you noticed, the boiling point for different substances is different because they have different intermolecular forces of attraction. Ethanoic acid has stronger intermolecular forces of attraction than water, and so therefore ethanoic acid stays in the liquid phase, does not boil until a temperature, well, each one of these increments here is 5 degrees, so we're going 5, 10, 15, about 17 and a half, so 117 and a half degrees Celsius is the boiling point of ethanoic acid at normal atmospheric pressure. Okay, so all of these have different vapor pressures. Acetone or propanone, way over here, that's going to boil at normal atmospheric pressure. It's going to boil. It's going to start boiling at 55 degrees Celsius. Now, that's a warm temperature, but nonetheless, that's not super crazy hot. Our body temperature is 37 degrees Celsius, okay? So if you've ever gotten acetone on you, immediately it feels cold on your skin. That's because what it's doing is it's changing from the liquid phase into the gaseous phase, and it's called the evaporative cooling effect. It's no different than when you get out of the pool or out of the shower and there's a fan blowing or something, and all of a sudden the breeze blows by you, and your wet skin, the water starts to evaporate off your wet skin. It feels cold. That's the same thing. It's the evaporative cooling effect. It's just at a less degree with water than it is with acetone, and it happens at lower temperatures. So when you get your acetone on your skin, it's going to change from the liquid phase into the vapor phase. It's going to pull some heat off of you because that's an endothermic process, and it's going to feel cold and it'll boil. Now, one of the neat things about this idea is you can change the atmospheric pressure. So if you increase the atmospheric pressure, like we do in pressure cookers, like an Instant Pot, if we increase the atmospheric pressure to like 150 kilopascals, which is essentially 50% more, and I think that's what an Instant Pot does, increases the atmospheric pressure to about 50% higher than normal atmospheric pressure. And what that does is that allows these substances, and so instead of water boiling at 100 degrees Celsius, water is now going to boil at 100, 105, 110, about 112 degrees Celsius. Now, that may not sound like a lot, but that's a good 12 degrees Celsius is a substantial temperature change. That's the difference between 12 degrees, about 10 degrees. 32 degrees Fahrenheit is freezing. 50 degrees Fahrenheit, all right, that's a 10-degree temperature change in Celsius. Okay, so it's a substantial temperature change, and that's why substances are going to cook so much faster. Things are going to cook so much faster in a pressure cooker Instant Pot. Similarly, we could lower the atmospheric pressure, and if we lower the atmospheric pressure, all right, you can get a substance to boil at a much lower temperature. And if we were in class, I would show you this demonstration. We can lower the atmospheric pressure over a sample of water, and we can make water boil at room temperature. That's a crazy phenomenon. So I will be able to lower the atmospheric pressure way down to right about, oops, I missed it, right about there. So we're about less than 10 kilopascals. And when we do that in the classroom, and it's not hard, But when we do that, the water will boil in a jug. It will look like a regular boiling, but it's no hotter than room temperature water. That unfortunately is a demonstration we do it in class, and you guys have missed out on it this year. But that's a neat demonstration. So if we get back, we'll do that. So anyway, vapor pressure is very dependent upon intermolecular forces of attraction. The stronger the intermolecular force of attraction, the higher the the lower the vapor pressure. The weaker the intermolecular force of attraction, the higher the vapor pressure. Okay, so hopefully you got that straightened out. In this assignment, you're going to find something called the Table H question packet. What I'd like you to do is I'd like you to go through that Table H question packet, do the reading, highlight some important stuff. Here's like what I've highlighted here. Go through, highlight, take notes. There's plenty of space in the margins. And then there's questions on it. And once you're done highlighting and annotating and taking notes on it, on anything I've missed, you need to do those questions. Okay? So all this can be done through Kami. If you have any questions, please, again, contact me through either Remind, Schoology, the Schoology app, or Parent Square, Brave Square. All right? Great. Thank you.